All right. Hello, class. Mr. Pettibone here. uh, at about 10 o'clock last night, I did your guys' quiz, or I finished writing your guys' quiz. So uh, feel free to start that. Note that the last quiz is due on Thursday at 11:59 p.m. That is to give me enough time to grade them all. So that I can close out the grade book, hopefully by the end of the week. That's what I would like to do. Is I would like to just give everyone the grades and yeah. Let's see what else. Yeah, so check out the quiz. Let's see who's watching. Hey Justin. Hey Nick. Hey Alex. Hey Christian. Hey Alex. Hey Aisha. One thing I did want to say is I am volunteering. I believe next Monday I volunteered to help with senior checkout, so maybe I'll see some of you on Monday. All right. So let's get down to it. I want to remind you the formulas for the relativistic momentum. Hey, Rowan. Relativistic momentum of a massive particle is gamma mc, gamma mv. So this is the time component, and this is the space component. Okay. So there are a couple of, and then we could also write this as energy divided by c, and then momentum. So one of the things I wanted to look at here, just to help you guys out, is notice that if I take the space component and the time component and I divide them, I would get gamma mv over gamma mc. Okay. I'm going to move this camera closer. Which is just equal to v over c. So you can get the velocity of the particle by taking this ratio here. Okay. So this is for a massive particle. If you have a photon, the momentum is hf over c, hf over c. Now, one of the things I wanted to talk about, I'm going to be there Monday, and I think that I'm also going to be participating in some kind of like delivery thing. Like, I know that the school is going to deliver something to you. I don't know what it is, but so I'll be driving around town delivering stuff whenever that happens. I hope that wasn't a secret. Are you guys aware that you're having stuff delivered to you if you're a senior? All right. I might volunteer more. I don't know. It just kind of depends on how next week goes. All right. So one thing I wanted to mention is that the time component is always positive, but the space component can be positive or negative, depending on whether the particle is moving to the left or to the right. Okay? So let's just go ahead and do an example just to make sure that you guys know how to calculate this. Let's suppose that an electron travels left at I don't know, 70% the speed of light, 0.7 c. Calculate its relativistic momentum. So, first thing I want to do is I want to figure out what gamma is. Gamma is 1 over the square root of 1 minus v squared over c squared. So that would be 1 over the square root of 1 minus 0.7 squared. Okay. So that gives about 1.4. So gamma is 1.4. So then, and then the mass of an electron is 9.1 times 10 to the minus 31 kilograms. And then this velocity, if I convert it to meters per second, it's going to be 2.1 times 10 to the 8th meters per second, because the speed of light is 3 times 10 to the 8th meters per second. So 3 times 0.7 is 2.1. So that means that gamma MC is going to equal 1.4, hey Zach, times 9.1 times 10 to the minus 31 times C, which is 3 times 10 to the 8th. So that gives 3.8 times 10 to the minus 22 kilogram meters per second. Remember, it's momentum. It still has the same units. And then gamma MV is going to be, this times 0.7, 2.7 times 10 to the minus 22 kilogram meters per second. So that means that the full momentum vector is gamma MC, 3.8 times 10 to the minus 22 kilogram meters per second, and then gamma MV minus 2.7 times 10 to the minus 22 kilogram meters per second. Now, why did I put the minus sign there? That's because this electron is traveling to the left. So remember, the time component of the momentum, always positive. But the space component of the momentum can be positive or negative. Okay? Let's do one more example with a photon. Let's say a photon of frequency or I'll just say a photon has frequency equal to 2.4 times 10 to the 14th hertz. It travels right to the right. What is its relativistic momentum? So you can tell I keep starting to say for momentum. So I'm just going to call it for momentum, okay? Because that's what I'm used to calling it, as for momentum. Because it's, if we were working without any simplifications, there would be 4 dimensions, 3 space and 1 time. So for a photon, HF over C is the important thing that we have to calculate. H is Planck's constant, 6.6 times 10 to the minus 34. F is 2.4 times 10 to the 14th. That's a given. And C is 3 times 10 to the 8th. So this gives 5.3 times 10 to the minus 28 kilogram meters per second. So that means that the momentum, the forward momentum of this photon is 5.3 times 10 to the minus 28, 5.3 times 10 to the minus 28 kilogram meters per second, kilogram meters per second. All right. So notice notice that the space component is positive because this photon is traveling to the right. Okay. So one other thing I want to, so that we have two theoretical pieces that I want to talk about, and then the lesson will be done. The first thing I wanted to talk about is kinetic energy. Hey, James. So remember, I told you that the actual formula is not E equals mc squared. It's E equals gamma mc squared. Okay. Can you hear me? It says, why did you say muted? Can you not hear me? So this is the total energy. Now, the energy when you're at rest would be the total energy evaluated at a velocity of 0. Okay? Now, if your velocity is 0, then that makes gamma equal to 1. So your energy when you're at rest is just mc squared. Okay? So how do we get the kinetic energy? Well, if we take the total energy and we subtract the energy that you have when you're at rest, then that would equal the energy due to the motion, right? Which is just the kinetic energy. So basically, we want to take this number and subtract this number. And so the relativistic formula for kinetic energy is gamma minus 1 times mc squared. So this is the real formula for kinetic energy, if you will. And what's interesting is if you take gamma minus 1, so you do 1 over square root of 1 minus v squared over c squared minus 1, you can do a Taylor series expansion to that, and the first term in the Taylor series expansion gives you the 1/2 mv squared for kinetic energy, but then it gives you corrections. There's relativistic corrections to the formula for kinetic energy, so it's kind of cool. So, you know, sometimes in physics, what you'll do is you'll calculate the answer assuming that the particle is not relativistic, so you just use the regular 1/2 mv squared. But if it's a little bit relativistic, you can include another term from the actual formula for kinetic energy and get a slightly more accurate answer. So it's kind of neat. All right. The next thing I wanted to talk about is the Doppler effect. Okay. So the Doppler effect, and this is the Doppler effect for photons. Okay. So I'm just going to assume for this problem that h over c equals 1 for this problem, because it's not going to affect the answer, but it's going to make the formulas more messy in the intermediate steps. So I'm just going to set h over c equal to 1. So then if we think about the momentum of a photon, or the form momentum of a photon is just going to be F. Because I said h over c equals 1, so the h over c part is just 1. I'm going to make this photon traveling to the left, so I make its space component negative. Okay? So this photon is traveling to the left. And here's the observer. Okay? What if the observer started traveling towards the photon with a velocity v? That's going to affect the so we'll have we'll have someone who's just sitting here watching all this happen. This person sees the photon as having a frequency f. But because this person is in relative motion, they're moving to the right, they're going to see a Doppler shifted photon. Okay? Doppler effect, because the person is headed towards the photon, they're going to have the frequency shifted up. Okay? The frequency is going to be higher. So how could we calculate what frequency does this dude measure? What frequency do they measure? And so to find the answer, we have to do a Lorenz transformation to the reference frame of this person. So this person is traveling to the right with speed v. So I'm going to use the Lorenz transformation matrix for that, which was gamma minus gamma beta minus gamma beta gamma. Okay? And so this will give us the momentum vector of the photon according to this dude. Okay? So if I do the matrix multiplication, you go like this. What you get is gamma f plus gamma beta f and then you get minus gamma f minus gamma beta f. Okay? So this would be the form momentum that this person measures. So that's just going to be equal to, remember, the form momentum of a photon is just hf over c minus hf over c. Okay? So this is just going to be f prime f minus f prime. You get what I'm saying? Where f prime is just the frequency that this person observes in their reference frame. Okay? So the answer is just as simple as this. Okay? What this says is that the frequency that this person observes, okay, is equal to gamma plus gamma beta. So I'm just matching up these two terms. Times the frequency that was emitted. Okay? So that equals gamma times 1 plus beta. And if you recall, gamma was 1 over the square root of 1 minus beta squared. So we have that times 1 plus beta. Now I'm going to write, I can write 1 minus beta as 1 minus beta squared. I can write it as 1 plus beta times 1 minus beta. You guys ever learned that one in your math class? Difference of squares. So that's going to give a final answer of the frequency observed is going to be square root of 1 plus beta over 1 minus beta times the frequency emitted. Okay, so this is the formula for the Doppler shift for photons. It's kind of cool. Okay, and this is in the case of blue shift. So in this case, the frequency moved up. But if the person was traveling in the opposite direction, you would make this a minus sign. All right, so that's pretty much my lesson. So you're going to use that formula to calculate the blue shift of photons. And you would just make beta negative if it's traveling in the opposite, if the photon is traveling in the opposite direction. I'm going to answer Alex's question really quick. Alex asks, what does the Lorenz transformation matrix look like for a 4x4 matrix? And so if you have a 4x4 matrix, it's pretty much the same. This would be a Lorentz transformation in the x direction. But then in this block for the y and z components, you just have the identity matrix. Okay, so this would be a boost in the x direction. If you had a boost in the y direction, you just you would have this would be a boost in the x direction. If you had a boost in the y direction, it would be gamma 0, 0, 1 0, 0, and then this would be like that. So you just that's how you do it for those other ones. All right, so that's my lesson for today. I hope you have a great afternoon. Tomorrow we're going to learn about the conservation of energy and momentum in relativity, and that'll be the last lesson. We'll have a meme review on Friday. I don't think anyone's submitted any memes, so if you have some memes, submit them, and have a great rest of